In previous sections that we've looked at in terms of the derivative and tangent lines, what we did is we found the tangent line, the slope of a tangent line, and the derivative at a particular point. But what we're going to be doing in this section, we're going to be working with the derivative as an entire function. Now, one of the advantages of finding the derivative as a function is it allows me to plug in a point or several points to determine what's happening with slopes of tangent lines, instead of having to go back from square one to figure out what's going on with each of those points. Now, in order to do this, we need to make sure that you know what the limit definition of the derivative is. So the limit definition, and we've already kind of derived this in the previous section, but we worked with this at a particular point. So the limit definition of the derivative, we will definitely need to have this memorized. You'll need to know it for tests and quizzes. Is the limit, actually let's go ahead and back up a little bit. Let's use this notation. F prime of x, notice that we're not using x naught here because we're not working with a particular point. The derivative f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so memorize, very important. Now, those of you who already know the shortcut rules for finding a derivative, on the first exam, everything we're doing is a limit definition of the derivative. We're not using any of those shortcut rules at all, so you need to know how to do this process. Again, if you want to check your answers using those shortcut rules, that's great, but only credit will be given for solutions found using the limit definition of the derivative. So definitely get this memorized. Now, hopefully you'll use it often enough that it'll be familiar with you without having to sit and try and figure it out and memorize it. Now, a couple other quick notes. Derivative notations. Now, we've talked about f prime of x for our notation, but sometimes you'll see a derivative written as dy dx, and there's also some other notations like a capital D lowercase x, and then you would have the function here. Let's say x squared plus 2x plus 1, something like that. Okay, and so all of these mean derivatives. Now, we can also take multiple derivatives. Now, typically with multiple derivatives, we're working with shortcut rules, but I just want you to be aware that you can find multiple derivatives using the limit definition of the derivative as well. And with multiple derivatives, what you do is you just keep taking derivatives. The second derivative would be the derivative of the first derivative. Okay, so the second derivative we would denote f double prime of x. And of course you can guess that the third derivative would be f triple prime. The fourth derivative, we're using Roman numerals here, would be f iv of x for the Roman numeral 4. Now, in terms of the dy dx notation, the second derivative is denoted as d squared y dx squared. This means second derivative. And of course, down here you can see with this notation you have a d and then two x's to represent second derivative. But again, these are the two most common ones. So most of this lecture we're going to spend actually finding these derivatives. Now, much of this is not calculus. The calculus only comes into play at the very end of these problems. Most of it is a lot of algebra. So you have to be pretty slick with your algebra. I would encourage you to show all your steps. That way you won't make any silly mistakes. Don't forget your basic algebra rules. So for this first problem, let's go ahead and find the derivative of the function f of x equals x squared plus 9x using the limit definition. So we have to use the limit definition here. Okay, so let's go ahead and write the limit definition. Now, when we write this, you never should drop this left-hand side. As we work through this problem, you never drop f prime of x, and you never drop the limit notation until after you've taken the limit. So what we do here to get started is we actually just write down the formula that we're going to be using. So this is our formula, and what we're going to do now is to populate the formula with the values that we're given. So notation, don't drop f prime of x. That's what we're trying to find here. This is not our function f of x, this is f prime of x, so you should not drop that notation. We haven't taken a limit, so we need to include the limit notation as well. So to get started, this says f of x plus h. That means everywhere there's an x up here, we put an x plus h. So that's going to look at x plus h quantity squared plus 9 times x plus h. So this piece right here is f of x plus h. Now what we need to do is subtract f of x. And again, I'm just following through with the numerator here. You need to put up your brackets for grouping symbols to make sure that the negative distributes properly. Now when I subtract off f of x, I'm just subtracting off the function. So that's x squared plus 9x. And this is all over h. Now real quick, if you took a limit here, you would get 0 over 0, which is indeterminate. Indeterminate means to do more work. So we do get 0 over 0, which is indeterminate. Indeterminate implies to do more work. And the more work that we're going to do is simplify the heck out of this thing. Now, keep in mind a couple of other things. The problem with this is this h right here. If this h wasn't there, I would not have a 0 in the denominator, and I wouldn't have the problem of an indeterminate form. So I need to get rid of the h. The only way I can get rid of the h is if it cancels with a factor, not a term, but a factor of h in the numerator. So my hope is, and this will happen every time you work these problems, once I expand, simplify, combine like terms, cancel up here, everything that's left will have an h in it, factor out an h, cancel, and kind of go from there. So let's go ahead and expand this. If I expand x plus h quantity squared, I get x squared plus 2xh plus h squared. Distribute the 9, distribute the negative. This is all over h. Now again, it's our great hope that everything without an h goes away. So 9x, negative 9x, and I believe we have accomplished our mission here. Again, don't drop your notation here. Now in the numerator, I'm left with 2xh plus h squared plus 9h. So those all have an h. So I factor out an h, and then I see here that the h's cancel. Don't drop your limit notation, don't drop your derivative notation. So now I'm left with taking the limit as h goes to 0 of 2x plus h plus 9. Now as I take that limit, the limit of these values, 2x and 9, those are just constants. They're not changing. The only thing that's changing here is the letter h. So 2x and 9, the limit of a constant is a constant. Here h is going to 0. And what I have then is that f prime of x is equal to 2x plus 9. And this is my derivative. Okay, and that's what I was trying to find. Now this function describes the derivative at any point of x, and all I need to do is choose some points of x, and then from there I can just find the slopes of the tangent lines, instantaneous rates of change, equations of tangent lines, and all sorts of other good stuff. Let's go ahead and look at this problem again. Remember, our original function was f of x. Make sure that doesn't look like a prime mark. My original function was f of x equals x squared plus 9x. And what I determined was f prime of x is equal to 2x plus 9. Okay, so again, this is the derivative. Okay, well, what is the derivative? Well, the derivative can be a lot of things. It can be an instantaneous rate of change. It can give you the slope of the curve. Another way to say the slope of the curve is to say the slope of the tangent line. So it's giving you all these things, but at any value of x. So that's the important thing to remember here, is at any value of x. So this is my derivative. So if I wanted to, I could figure out, okay, well, what's the slope of the curve at, let's say, x equal 2. Okay, well, the slope of the curve at x equal 2 would be f prime at 2, which is 2 times 2 plus 9. 4 plus 9 is 13. So in this case, the slope of the curve is m equal 13. I could also talk about the instantaneous rate of change at x equal negative 4. So I'd have f prime at negative 4, 2 times negative 4 plus 9. Negative 8 plus 9 is 1. And this would be, since it's instantaneous rate of change, let's say meters per second, or something similar to that for an instantaneous rate of change. So again, that's what I can do with this nice function then that describes the derivative at any point. Couple quick things. Don't ever drop your notations here, because I'm going to have not only a function running around, but a first derivative and possibly multiple derivatives. So again, don't drop your notation as to what these values are of x squared plus 9x and 2x plus 9. So again, all of this was algebra except at the very end where we actually started taking a limit. Let's go ahead and look at another example. Same directions, different function. Find the derivative. And let's use a really nice little easy function here. Find the derivative of f of x equals 1 over x using the limit definition. So again, I would always encourage you to write down what the limit definition of the derivative is. That is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Now what we want to do is to populate this equation. Again, do not drop your limit notation. Do not drop your f prime notation. Now what this means, f of x plus h, it means everywhere there's an x here, we plug in an x plus h. Minus f of x means to subtract my original function all over h. Now, avoid this error. A lot of people say f of x plus h for this function, and this is not true, is 1 over x plus h. But this h actually has to go into the denominator. So avoid this error. It's not a good one to make. So working down here, if I took the limit as h approaches 0 right now, I would get 0 over 0, which is indeterminate. Indeterminate means to do more work. And we know the work we have to do here is I need to get rid of this h in the denominator. I have to. Because when I take the limit as h goes to 0, I'd want that 0 out of my denominator. So what I do here is I try and find a common denominator. Now watch this very closely. You guys have done this in algebra so many times, but it's really a good spot to be able to make a mistake, so you have to be careful. I'm going to take this h and rewrite it as h over 1. Now my common denominator up here will be the product of x plus h and x. So if I think about it, I need to multiply top and bottom by x here. Here I need to multiply top and bottom by x plus h. So I get x minus the quantity, here's the minus, the quantity, x plus h. Now what's my common denominator? X times x plus h. Okay, so f prime of x, don't drop your notation. I'm going to distribute this negative, and I'll have x minus h all over. Okay, now this is what we're going to do with this one. I have an x times x plus h here, but what about this h over 1? I want to get rid of these layered fractions. Well, the rule is this. When you divide by a fraction, you multiply by the reciprocal of the fraction. So we want to multiply by the reciprocal of h over 1, which is 1 over h. So f prime of x equals the limit. Don't drop your functional notation for the derivative, and do not drop your limit notation. Notice that the x's cancel here. X minus x is 0. And I'm left with a negative h all over x times h times x plus h. Now I could have canceled right here if I wanted to, but I want to show you how this rewrites into the denominator, because it's pretty common to flip it right away and just stick it in with the denominator. So again, this h right here is now over here. Now the h's cancel, and again that's what I want to have happen, because that h in the denominator is what's causing the trouble. And I'm left with a negative 1. Don't forget there's a negative 1 here. X times the quantity x plus h. Now if you wanted to, you could distribute the x, but there's really no reason to. We want to take the limit now as h goes to 0, and just this one piece goes to 0. So what I'm left with here then is that f prime of x equals, I don't want to drop my derivative notation, but now I can drop my limit notation because I've taken the limit. I'm left with a negative 1 in my numerator, and in my denominator I'm left with x times x, which is x squared. So f prime of x equals negative 1 over x squared is the derivative of f of x equals 1 over x. So again, lots of algebra. There's actually very little calculus going on here except for that limit at the very end that we look at. Now again, this negative 1 over x squared is the slope of the tangent line anywhere on the graph of f of x equals 1 over x. The only thing I need to do is to come up with a point to try and describe that. Let's go ahead and look at some other examples. And then also, I want to talk about graphing these in Maple and then talking about equations of tangent lines as well. So let's go ahead and look at a quick example. Lots of algebra. These are fun problems. So let's go ahead and find the equation of the tangent line to the function f of x equals, let's just do square root of x to make this one easy for the first time, at the point x equal, let's do 4. So if we wanted to, we could actually go through and find the derivative at 4 like we did in the previous section, but I'm going to do this, the derivative as a function, first, and then show you how this problem works from there. So first of all, to write an equation, I need two things. I need a point and I need a slope. Well, the point, we are given the x coordinate right now of 4. Well, if x is 4, I can plug this into my function. The square root of 4 is 2. So the point is 4, 2. And what we need to do now is find the slope by taking the derivative and evaluating it at 4. So now that's why it's so important to not drop your notation here of f of x and f prime of x, because we have so many functions running around, we can't confuse which one is which because it will affect our solution. So let's go ahead and do the f prime of x, and then when we get all done, we'll plug a 4 in. Now again, we could find f prime of 4 directly. I just want to do this one a little bit differently. So limit as h approaches 0 of f of x plus h minus f of x all over h. So here's our formula, and let's go ahead and populate the equation. F prime of x is equal to the limit as h approaches 0 of f of x plus h. The entire x plus h must appear under the radical because my function x appears under the radical, minus f of x all over h. Now if you take a limit right now, you'd get 0 over 0, which is indeterminate. Indeterminate means to do more work. Well, let's talk about the more work that we can do here. Looks like to me that we could multiply by a conjugate. So let's go ahead and look at x plus h minus root x all over h, and then the conjugate. Now the conjugate will be the conjugate of the numerator, of course, so that would be a plus root x. And whatever you do to the bottom, you have to do to the top. Basically what I've done here is multiply by 1, the multiplicative identity. So here we have f prime of x is equal to the limit as h approaches 0. Now when I work with this binomial times a binomial, and they're conjugates of each other, I have to FOIL it out firsts. And then what happens is your outsides and your insides will sum to 0. That happens every time you work with conjugates. And then I'll have my lasts as well. So my first would be x plus h. Root x plus h times root x plus h is just the radicand back. Outsides and inside terms go to 0. I guess we could show that. So here's my outsides. Here's my insides. So here again is my outside. Here's my firsts. Outside, insides, and then we have my lasts. I have a negative times a positive, which is a negative, root x times root x, which is x, and this is my lasts. And this is all over h times the quantity, because the h has to distribute, so you need to have a bracket up there. And again, it's my fond hope that something will cancel here. Now there's really no reason to distribute that h because I want it to cancel. Now, as we said before, outside and insides go to 0. Here's x minus x goes to 0. And I'm just left with a nice little h in the numerator. And that's exactly what we wanted to have happen because I need it to cancel. And when these cancel, I'm left with a 1 in the numerator. And again, don't drop your limit notation. We haven't taken a limit. Now when I take the limit, this piece goes to 0 right here, and I'm left with f prime of x equals, I've taken the limit now, so drop the limit notation. Root x plus root x is 2 root x. This is the slope of the tangent line to y equal root x at any point on the graph. Now notice y equal root x, that's just working with values of x that are 0 or larger, so I couldn't use like a -2 or anything here because then I'd be working in the complex number system. So this is the tangent line to y equal root x at any point along the graph. And as just a quick side note, another notation I can use for f prime of x is y prime. So I could also say y prime equals here. Well, we want the slope at x equal 4. That was given to us in the original problem. So the slope at x equal 4 is f prime of 4, which is 1 over 2 root 4. Square root of 4 is 2. 2 times 2 is 4. So there's my slope. So recall the point was 4, 2, and now our slope is 1/4. And I put this in the point slope form of the equation, and I'll have the equation of the tangent line. So I have y minus 2 is equal to 1/4 times x minus 4. Y minus 2 is equal to 1/4 x minus 1, 1/4 times 4. And then I'm going to add the 2 across. So I have y equal 1/4 x, and when I add the 2 across, I'll get a plus 1. So this is the equation of the tangent line. To y equals square root of x at x equal 4. Okay, so what I would like to do is to check to see if this makes sense by using Maple. So let's go ahead and pull open Maple, and let's go ahead and look at some graphs. Our first graph is square root of x. So here's my square root of x. Whoops. Now if you don't remember how to do square root, remember you have your expressions palette over here, and under the expressions palette, if you hover under the square root, it kind of gives you the SQRT there. Now the equation of the line that we came up with was y equal 1/4 times x plus 1. I believe that's what it was. Let's have a look. 1/4 x plus 1. Yep. So what I would like to do is plot both of these. And then I'm going to drag one on top of the other and see if they look like tangent lines. So let's go ahead and look at the plot here first. And then I'm going to plot this one. And again, you can use a plot command as well. I'm going to change the color of this just so I can distinguish between my original graph and my tangent line graph. I'm going to drag and drop one on top of the other. This really does look like a nice little tangent line, and it looks like it is tangent at 4. So I'm going to go ahead and grab this, and let's go ahead and pop it into our notes. So again, what it looks like we have here is our original function is in red. So here's y equals square root of x, and here's the tangent line, and it does look like a tangent line, so I think we're on the right track here. And the tangent line was y equal 1/4 x plus 1, and it's supposed to be tangent at 4. Goes straight up here, and that looks reasonable. In fact, it's tangent at the ordered pair 4, 2. So you can kind of look at these in Maple as well to check and see what's going on here. Now Maple is also nice in that you can check your limit notation. Over here in the expressions palette, you might have noticed there's a limit notation. Let me get down to a point here where we can enter something. So here I have my limit notation. Now if I wanted to use this same expression that I've been working with, and that would be SQRT x plus h minus SQRT of x divided by h. Oops, I better go through and make sure I have parentheses around both terms of my numerator. What ends up happening here is you need to remember the limit definition takes the derivative as h goes to 0. So I need to come over here and change this notation. H needs to go to 0, not x. So as h goes to 0. So let's see if I have everything entered correctly here. And I do. I get 1 over 2 root x, and that's actually my derivative. So I'm going to snap that out of here and throw it into our notes as well, just as a quick note to remind us how to find limits. And of course this limit is the same as the derivative. So this piece right here is the difference quotient. This is the limit as h approaches 0 of f of x plus h minus f of x all over h. And for our particular case, we were using f of x equals the square root of x. And this is our notation for f prime of x. So we can check these solutions as well in Maple. So, one more time, we've been doing a lot of algebra. A lot of these are just a lot of very repetitive algebra. And the way you can avoid making mistakes with these problems is to make sure that you show all your work, don't drop any notations, don't take any shortcuts. Now just to introduce one more notation with the problem that we just did, sometimes what we'll see is when we're trying to take a function and evaluate it at a particular point, for instance, we're looking for f prime at 4, sometimes what you'll do is you'll see that written as the derivative of my function y with respect to x evaluated at x equal 4. So that's another notation that you can see here. And sometimes I'll also say something like f prime of 4 is equal to the derivative with respect to x, and then they'll put the function in here evaluated at x equal 4. So basically they're assuming y is equal to your function, y in this case is equal to f of x equals square root of x. So again, these are all different ways that you'll see these types of problems worked. Now there's a couple other things that we need to talk about in terms of continuity, differentiability, and right hand and left hand derivatives. The first thing that we need to remember here is that if I have a function that is differentiable, or we could say it has the characteristic of differentiability, differentiability implies that I have a continuous function. It implies that I have continuity for a function. But this does not work the other way. So for instance, if I have a continuous function, that doesn't mean that it's differentiable at every single point. Some problem areas that we can have for differentiability are cusps. This is an example of a cusp. Right here at this point, again, we'll call this a cusp. I would say that this function is differentiable on the left-hand side and the right-hand side, but it's not differentiable at the exact cusp. Because remember, the information that a derivative provides is the slope of the tangent line. Well, which tangent line do I have here? This is like a needle coming to a point. And if you talk about ways that I could skim the top of that, there could be a tangent line here, there could be another one here. There's an infinite number of possible tangent lines. And so I can't just choose one of them to work with, because again, it's that sharp point. So I don't know which of those is the true tangent line, so I don't have differentiability at that point. So when you have a graph that has a cusp like that, that happens as well, that I am not differentiable, even though this is continuous. Another one that we can talk about is an absolute value function. Now it doesn't come to a cusp like this one, but it does come to this sharp point. And again, this is something like, let's say, the absolute value of x. Same problem. Which one is the tangent line? Well, they all are. So how do I find the slope of them? There's an infinite number of tangent lines here, and so I have a problem in that area. So remember, differentiability does not always mean that a function will have only one slope of a tangent line at a point, so I have to be careful here. If I have a continuous function, that doesn't mean it's differentiable at every point. However, if it's differentiable, that implies that it's continuous. Now another curve that I'll have difficulty with is something like a curve like this. Now at this point, I can tell that I have a tangent line right here that has a slope that's going to be completely vertical, and so what we say there is the slope is undefined. So if I have basically the tangent line having infinite slope, that would mean that I have a problem with differentiability there at this particular point as well. So you're going to run across a few cases like that, and just keep them in mind. They're not absolutely very common, but you do need to keep in mind that there could be a potential problem there. Now, another problem that I like to be able to look at and work with these types of graphs is I like to be given a slope and then say, you know what, with this function, figure out where it has that particular slope. So another type of question we could ask is something like, where does the slope of the graph f of x equal, let's say, square root of x equal, and we can just choose any value we want. Let's go ahead and choose for the slope to equal 1/8. So what I know here is the slope is equal to 1/8. Well, if you recall, f prime of x gives this slope information, and we already calculated this to be 1/2 root x. Now we want this slope to be equal to 1/8. Well, one way to solve this would be to cross multiply, and I have 2 root x equals, cross multiplying, 8. Dividing through, I get root x equal 4. Squaring both sides, I get x equal 16 here. So what this is saying here, at x equals 16, and if I plug 16 into my original, square root of 16 is 4, I will have a slope of the line, or the slope of the tangent line, equal to 1/8 at that point. So, and again, if we wanted to, we could go through and we could try and verify this with an equation of the tangent line at this point now, kind of work backward and plot not only the original function, but the equation of the tangent line as well. So function is f of x equals square root of x. And then now we also have a point and a slope. So we have y minus 4 is equal to 1/8 times x minus 16. Y equal 1/8 x. Distribute the the 1/8 to the negative 16, and I'll have a negative 2. Add the 4 across, and I have y equal 1/8 x plus 2. So this is the slope, the equation of the tangent line at 16, 4. It does have a slope of 1/8. So I want to pop Maple open again and see if this is going to match up with what we think should be going on. So I think our original function was square root of x. Let's go ahead and plot that one. Again, you can use a plot command as well. And we came up with the equation of the tangent line, slope of 1/8 x plus 2. So we have 1/8 x plus 2. We want to plot this. Again, I want to change the color of this just so it's comparable, so I can remember which is which. And I'm going to drag and drop this one over here. And whoa, we got a little bit of a problem here. Well, let's look at this ordered pair. Our ordered pair was 16, 4, and if we look at our scale here, our scale's not even hitting 16. So let's go ahead and look at our graph. There's no sense in having negative values here because square root's undefined in the real number system. So let's go ahead and change these values, let's say horizontally from 0, and let's go to 20. Okay. It looks like for this one, we'd have to scale it out as well. It's not changing this graph for us. But we can see here that when it skims across, it does look like it's 16 that this would be happening. So I think it's because of the way we pulled it in. Let's see if we can fix it down here. Change our color. This might not work. It just won't go that far for whatever reason. Let's change the plot first down here. Let's go 0 to 20 on this one. And I bet that'll fix it. Huh. Made it even worse. So 0 to 20. There. Now why wouldn't it want to plot 0 to 20 here? And let's change our vertical then. Yeah, going to 0 is fine, but let's go ahead and go up here to, let's say, at least 20 as well. Okay, now let's put it up there. I'm going to take the old one out and drop the new one in, change its color. Again, this is all trial and error. I would encourage you to just work through problems similarly. I don't know if it's going to work, but I'm going to give it a shot. Yep, we got it to go. And it might even be nice to go further out because it almost looks like the same line. But if we change the scale on this and extended it, we would see that it would skim across the top here. So let's go ahead and pop that in to our lecture notes. And this is kind of indicating exactly what we were trying to come up with here. So the slope is 1/8, and this is occurring at the point 16, 4. So here's 15, here's 16, 4. And you can see here's our point 16, 4. Whoops, not 16, 14, 16, 4. And here's my tangent line. It has a slope of 1/8. It y-intercepts at 2. So this is a line y equal 1/8 x plus 2. So I found where I have the slope of the tangent line, or the slope of this curve, equal to 1/8. So that kind of verifies that information for me. So make sure you have Maple open, trial and error. It kind of helps you out a lot to visualize things. You will not have Maple or calculators on your exams, but it still helps you try and understand visually what's happening with these functions.